Here we go. One of physics' most famous experiments is the double slit experiment. Sometimes it's called the Young's experiment after that Thomas Young guy. It was a big deal for a whole bunch of reasons. Um, One of the reasons is Young was a British guy. Thomas Young was British. This other British guy named Newton, he published a whole bunch of papers saying that light was a particle. And his papers seemed to be matching what people saw. He had a way to explain interference. So he had all this cool stuff. Um, and then this young guy, literally this young guy named Young, another British guy, came along and his experiment said Newton couldn't be right. Newton's, sorry, I said it wrong. Newton's worked really, really well, but it didn't explain interference very well. So when Young came along and did this experiment, he proved that light had to be a wave, and Newton had set up all his stuff saying light was a particle. So it was kind of a big deal at the time that this literally young whippersnapper proved Newton wrong. It'd be like 10 years while Einstein was just after Einstein passed away, you tried to prove Einstein wrong. So it was a big deal at the time just because it flew in the face of what Newton had said, and the outcome is still talked about today. Like when we get to quantum physics, we're going to come back to this double slit experiment and talk about it again. So here's what Young's brilliant idea was. Basically, he created two very small slits in a he painted a piece of glass black so that no light would go through it. Then he scratched in these two really narrow sources of slits, and then each of those sources is going to act like their own light source, and we should see an interference pattern on the screen beside it. In this day and age, we use lasers, but way back in Young's time, they would just use sunlight. In that Veritasium video you watched, that's why they got kind of the rainbowy effect. Basically, we needed two sources of light emitting one color by using a laser pointer and having these two slits really close together. Each slit acts like its own source of light. Because they're illuminated by one light source, like the laser pointer, that locks them in phase with each other. If we build it carefully, or Thomas builds it carefully, scratch these lines into the piece of glass really close together, we can get them comparable to the wavelength. And we're going to scratch in narrow lines so that they're small, so we can hit all that stuff we talked about before. This weird artificial scenario. We wouldn't get the interference of light from two headlights of your car. So you don't have to worry about like driving home at curfew, dark outside, you flip on the headlights of your car. You don't have to worry about the two headlights of your car overlapping and creating destructive interference and creating a dark spot right in front of your car. The two headlights would not be locked in emitting one color. They definitely wouldn't be in phase. They're definitely crazy far apart compared to the wavelength of light. And compared to the wavelength of light, each headlight is really huge. So the only way we'll get interference of light, since the wavelength of light is tiny, we have to have tiny slits that are really close together. Then we'll see the interference of light. So in this contrived scenario, I've got some pictures in a later note where I'll show you what the equipment looks like, but it's basically what this thing kind of looks like. A piece of opaque material with two narrow slits scratched or carved into it. The whole key to interference is going to be, and this is what the note's going to be about and what the video kind of outlined, is that the light that hits the screen comes from two slits. Light from one slit, light from the other slit. They don't necessarily travel the exact same distance. Light from the one slit is going to travel farther than light from the other slit. Whether it's bright or dark depends on how much farther the light from the one slit traveled compared to the other slit. So in this little blurb, from now on we can think of each slit in the double slit experiment as our source. So here we go. I'm going to try and explain the math of this. I've typed it. I'm going to talk you through it. Hopefully this kind of clicks. If we have our laser on the left, hitting our double slits over here, light travels through the one slit, the top slit, light travels through the bottom slit. A whole lot of light goes through those two slits. Out of all that light, let's just focus on the light that travels and hits at this point right there. I'm going to call that kind of on the reference line. It hits on the perpendicular bisector to the two slits, so it kind of hits in the middle of the screen. The light that traveled from the top slit, I'm going to kind of mess up my diagram, this light from the top slit travels the exact same distance as this light from the bottom slit. Basically, it's like a sideways isosceles triangle. This top line is exactly the same length as this bottom line. Since they travel the exact same distance and they started off in phase with each other, if it's like a crest of wave from the top slit, it's going to be a crest of wave from the bottom slit. Or if it's a trough from the top slit, it's going to be a trough from the bottom slit. Since they're traveling the exact same distance and they started off in phase, when they get to that point, they're still going to be in phase with each other. Since they're in phase with each other, that point is going to be a bright spot. So if we shine light on a double slit, that point on our reference line, this point is always going to be a bright spot because the light travels equal distances. Traveling equal distances means it's in phase. But there's some light, so out of all that light that goes through the double slits, if we consider a point up here, let's say, I could have chosen a point below the reference line, but I just happened to choose a point above the reference line. Basically, any point that's not on the reference line, the light from the one slit has to travel farther than the light from the other slit. In this case, the light from the bottom slit travels a little bit farther than the light from the top slit. The logic is, if the extra distance that the light from the bottom slit traveled is half a wavelength, if this little bit down here, this little extra bit farther that this one traveled compared to the top one, if it's half a wavelength, then if it's a crest from the light that came from the top slit, if it's half a wavelength difference in distance, then it's going to be a trough from the other one. When you're off by half a wavelength, if it's a crest from one, then it's going to be a trough from the other. Or if it's a trough from one, it's going to be a crest from the other. But if it's a half a wavelength in difference, basically what it means is that those two lights that get there are out of phase with each other. Out of phase means it's going to be destructive interference, means it's going to be a dark spot. Or maybe this point on the screen is so far away, the difference, the point is at this point on the screen over here is at a point where that extra distance I talked about, instead of half a wavelength, maybe the extra distance is a full wavelength. If the extra distance is a full wavelength, then if it's a crest from the one slit, it's also a crest from the other slit. If it's a full wavelength, that kind of puts them back in phase. If it puts them back in phase, that means it's going to be a bright spot. Or maybe that point we're looking at on the screen is such that the extra distance is 1.5 wavelengths. If it's 1.5 wavelengths, then a crest from one would be a trough from the other. That's back to being out of phase. That's basically the same as if it was just half a wavelength. If the extra distance was 2 full lambdas, that's kind of like the same scenario as 1 full lambda, then they're going to be in phase with each other and it's going to be a bright spot. So what's going on at a point on the screen, the way that I've drawn it, is all about this extra distance down here. How much farther the wave that came from the bottom slit compared to the top slit. If the extra distance is 0, that was this picture up here, or if the extra distance is 1 lambda or 2 lambda or 3 lambda, if that extra distance is a multiple of lambda, then the light from the bottom slit and the light from the top slit are in phase, and that's going to mean constructive interference or a bright spot. If the extra distance is off by a half, then that means they're out of phase, and that means the position is a dark spot. This is the logic of double slit interference, whether something's bright or dark. All about the extra distance. If the extra distance is a multiple of lambda, the light's in phase, therefore a bright spot. And if the extra distance is off by half, the light is out of phase, therefore a dark spot. Really moving forward, we just need to have an equation for the extra distance, and then we'll apply this logic. I'm going to pause this video because I don't want to get too long, and then we're going to tackle the math and we're going to try and come up with an equation for the extra distance so we can apply our logic.